Okay, so this is Unit 5, Lesson 2, Exponential Functions, and this is just some review from grade 11. So the first one here, we're going to look at exponential growth. So let's just think about the function y equals 2 to the x. So for exponential growth, the b value, which is the base, or the 2 in this case, has to be bigger than 1. So this is telling us there's a growth factor of 2. So then we could do a table of values to see what this function looks like. So we know that 2 to the 0 is just going to be 1. 2 to the power of 1 is going to be 2. 2 to the power of 2 is going to be 4. And 2 to the power of negative 1 will just be 1/2, and so on. So this function is going to look something like that. Okay, and we can see here that there's no value that you can sub in for the x, for the exponent. There's no value you can sub in that will make this function go below 0. So we can see that there's going to be a horizontal asymptote here at y equals 0. At y equals 0. And let's just state the domain and the range for this. So the domain x such that x is an element of the real numbers. So this function would continue to have larger and larger x values and smaller x values. The range, however, we can describe a little bit more. We can see that y is going to be greater than 0 and y is an element of the real numbers. Okay, so that's exponential growth. So as we read from left to right, it's increasing. So this would be like population increase. This would be like compound interest. So if you invest money, how your money grows at an exponential rate. Okay, so then let's look at decreasing growth. So let's think about, we're thinking about decreasing growth. Sometimes we call it exponential decay. So this could be something where something's depreciating in value, such as like a computer or a vehicle, or it could also be, there could be some science examples where something's decaying. So let's think about this example. So let's think about 1/2 to the exponent x. So the b value here, the decreasing factor is 1/2. So this is always the growth factor here. Okay, so if we use a table of values for this one as well, if we end up subbing -1 in, we'll end up with, once we invert and multiply, we'll end up with 2. If we sub 0 in here, we'll end up with just 1, because anything to the power of 0 just gives us 1. And then if we sub a 1 in, we'll end up with 1/2, and so on. So this function is going to look similar to the first one. And we could write this as so if we flipped it, we could write this as y equals 2 over 1 to the negative exponent, negative x exponent, sorry. So because remember when you invert and multiply, so 2 over 1 is the same thing as 1 over 2 to the negative 1. So using those exponent rules, we could rewrite this function as y equals 2 to the negative x. So we flipped this over, and we just need to change the exponent to be a negative. And so now if we look at these two functions, if we look at this one, and we look at this one, and if we think about our last unit, we know that this negative exponent up here, or a negative inside of the parent function, means that we're going to be reflecting around the y-axis. So it's a reflection around the y-axis, and we can see that that happens here. So this one's increasing, reflected around here, and this one's decreasing, and it's reflected around the y-axis as well. Okay, so let's look at some more transformations of these functions. Okay, so if we have a positive stretch factor, so let's say we have y equals, let's say we put an a value of 2 out front. So let's say we have y equals 2 times 2 to the x. So that's going to be like our last function above, but we're just going to be stretching out the y values. So you could pop that into a table of values again. What's going to happen is instead of being at 1 here, we're going to go up to 2. So it's just going to be a steeper slope or steeper increase. So then at 1, if we sub in 1 here, we'd end up with 2 to the 1 is 2 times 2, so that'll give us 4. So it's just going to be a faster increase. So this is just a vertical stretch by 2. And then let's look at another example here, a negative stretch factor. Okay, so let's see, if we had y equals, let's just put a -1 out front. So we're going to have the same graph that we had above this one, except for everything's just going to be reflected, just like what we've seen in all the other functions in this course. A negative out front means it's a reflection in the x-axis. Okay, so then we'd have, instead of having our first point up here, we're going to start down below. And the function will just be reflected like this. And you could use a table of values for that too. One a little wonky. Okay. Okay, so those are, so far we've looked at positive at stretches and vertical stretches, and if we have a negative out front. So now let's look at what happens if we have some vertical shifts. Okay. Okay, so let's say we had an example, y equals, let's keep a 1 out front as the stretch factor for now. So let's say we had the function 2x, and then we're going to add 2 at the end. So we know anytime that we add something at the end of a function, that's going to affect the vertical position. So that means that the horizontal asymptote is going to move up by 2. So if anything's added or subtracted at the end, it's going to move the horizontal asymptote up 2 in this case. Okay, so we're going to have a vertical asymptote at 2 now, and then all of our points will just follow the same pattern, but will be increased by that 2. So the function will look something like that. So here's our horizontal asymptote at y equals 2. Okay, so please take a couple minutes and sketch these 3 examples, A, B, and C, and I'll show you the answer to these, and I'll discuss them in a couple minutes, and then we'll look at the last example again together. Okay, so you may want to pause this for a little bit, give these a try, and when you're ready, hit play to see what the answers look like. Okay, so for this one, we can see that there's going to be an asymptote at -4. So there's my asymptote. And then I think the easiest way to sketch these quickly is to just do a couple test points. So we know approximately the function is going to look like this. If we pop a 0 in there, right away we can see this is going to be a 1 minus 4. So that's going to give us -3. And then I would just do a couple more test points. So maybe do -1 and +1, or -1, +1, +2 if you want to. So that's what this function looks like approximately. The next one, we can see the base in here is decreasing. It's going to be exponential decay, but we're going to have a stretch factor of 3, and we're going to have an asymptote at -1. So there's a -1 for the asymptote. And then if you just pop a couple test points in here, so if you sub -1 in here, you'll end up with 5. Yep, with 5. And then if you sub 0 in, and I subbed 1 and 2 in as well, just to give a more accurate picture of what this one looks like. And then the last one, we can see it's going to be exponential growth as the base, because the base is 4, but it's being reflected around the x-axis. So it would have started out if we didn't have that negative sign out front. The function would have looked like this as exponential growth, but because of this negative, it's being reflected around the asymptote. So we end up with the function being flipped or reflected. Okay, so last example, a population of 400 bacteria is growing at an alarming rate of 9% per hour. How many bacteria will be present in 24 hours? Okay, so I guess that asymptote is staying with us. There we go. Okay, so we want to think about how the 400 is the starting amount. So for all of these equations, we end up using a similar formula, and it's something like this, all the word problems. So, and the A is always the initial amount. This is always, the B is always the growth or decay factor. And then the X is usually the time in any of the word problems. Okay, so the 400 is going to be our A, or our initial value. It's growing at an alarming rate of 9% per hour. So we're growing. So we're thinking about exponential growth. So that means that if we think about 9% as a decimal, that's 0.09 if we divide it by 100. But we're growing, so we want it to be the amount we started with plus 0.09. So our B is actually going to be 1.09, will be our B. Okay, so here's our A and our B. So now we've got the A, the B, and then the time is just the 24 hours. Okay, so now we can pop this all in together. So the F at 24 hours, the function at 24 hours, is going to be the 400 we started with, and then the growth rate of 9%, we've got 24 up here. So it's really important when you pop this in your calculator that you do this first, because following BEDMAS, we want to do exponents. So we'll do this first, take that answer, and then multiply it by 400. So you may want to pause just for a second and give that a try, and make sure that you get 3,164.43. So therefore, in 24 hours, there will be 3,164 bacteria approximately. Okay, so next one, we're going to use the same equation, but this time we're being asked for how many hours until there are 6,000 bacteria. So this time we don't know what the time is. We know what the value is, though, is 6,000 bacteria. So we're just going to fill in the same equation. So we're going to have 6,000. We've got the 400 we started with at the 1.09, and we've got the x up here. Okay, so we want to get the x by itself. So the x right now is attached to the 1.09. So what we're going to do is divide both sides by 400. We're going to peel away that layer. So divide both sides by 400. And we end up with 15 is equal to 1.09 to the power of x. And in the next couple lessons, we're going to show you a way to use some buttons on your calculators to solve this. But for right now, just while we're reviewing grade 11, we are going to instead use guess and check. So you're just going to start trying to find different work to sub in for x. So you could sub in 1.09 to the power of 2, 1.09 to the power of 3, until you get to a value that gives you close to 15 as an answer. So you may want to pause, give that a try for a couple of minutes, or I will save you the time and tell you that the answer is approximately 32. So 1.09 to the power of 32 will give you approximately 15. So therefore, the bacteria will reach 6,000 in 32 hours. Okay, that's it for this lesson.